Now I'm taping. Okay. So extra credit number one is what is parallax, right? So what is parallax? So as we saw, parallax is not a distance from Earth to the Sun, because this is one astronomical unity, right? A shift in position of an object caused by the observer motion, is that the one? Or the change in distance, or the change in the distance to an object caused by the sun's motion? So which one it is? What's the most the best possible answer? So it's not a distance from Earth to the Sun. So, but the parallax, how about B? Is the shifting position of an object caused by the observer motion. So let's go back to here. So the observer is moving from here to there, and as a result we see twice of the angle we call parallax form. So it's caused by the motion of an observer as it goes around the sun. So it's not a change in distance, right? Because parallax allow us to measure distance. So C and D wouldn't be fine. So what is, that's the first question in our extra credit part. Now, those terms are important: brightness, apparent magnitude, absolute magnitude, and luminosity. So in the final exam, which is sort of a comprehensive, expected to have these questions asked in there. What is brightness? Brightness is a measure of how much of the energy the star sends out, or the galaxy sends out, you receive here on Earth. So brightness doesn't tell you exactly how much energy the object itself sends out, intrinsically speaking. Like the sun appears to be very bright, not because it has lots of energy, but because it's close to us. So brightness, although the sun is a star, it's kind of powerful, it's better than a lighthouse. So when brightness of a star, the brightness of a galaxy depends on two factors. One, how much energy itself that object is sending out. Second, it depends on how far that object is. So if I take a 100 watts light bulb and I keep one close to my eyes, and I take the other one and put on the top of a hill that happens to be miles away, of course that 100 watts light bulb will appear very dim if seen on top of a hill that happens to be miles and miles away. So distance affects how bright an object appears to you. Now, apparent magnitude is a scale astronomers develop, is a logarithm scale that is applied to the amount, the brightness received here on Earth, and certainly that number is very small, right? So what astronomers did, they select certain group of stars. They are called standard stars, and the brightness of the other stars are measured in comparison with these standards. So what boils down to our students, to you, is that the brightness scale in astronomy, the numbers are such that the smallest number represents the brightest possible object you have in view, and the smaller number is the biggest number is the brightest object. Did I say the other way? No, I said the other way. So again, the brightest object, you have a sample of stars out there in the sky. The brightest of them is the one with the least magnitude number, because of this logarithm scale. And the object that's the dimmest possible is the one that has the biggest number, biggest magnitude number. So one example, a object that is the limit of what you can observe has a magnitude 6.0. And Sirius, which is the brightest star in the sky, besides the sun, it has a magnitude that's a negative number. It's not even a positive number, it's a negative number, because it's one of the brightest objects in the sky. Now, absolute magnitude is, let's say you know the intrinsic brightness of the object, how much energy that object is sending out, and you place this object at 10 parsec, or at 32.6 light years away from you. How bright that object will look like in your magnitude scale. So that is the absolute magnitude scale, and that tells you another way of assessing energy production in that particular star or object. And the last one that I would like to mention is luminosity. This is the intrinsic brightness. This is the energy the object itself is sending out in space. This could be my extra credit question number 2. Out of these objects here, 1, 2, 3, 4, 5, which one is the faintest one? Which one is the faintest one? So again, the faintest one is the one that is, I don't even have a question in there, but the faintest one is the one that has the biggest apparent magnitude number, which is the number 2, right? The answer would be number 2. And out of these options, that's my question number 3. Out of this option, question number 3 for my extra credit, which I posted online as soon as I finished this tape. What is the brightest object in the sky among those 4? So that would be your negative 1.2, right? Should be the option number 3. Okay. Now, this is very important because it tells how light interacts with matter. So atoms, all the material that surrounds us right now is made of little atoms, and atoms they all have different properties. Like hydrogen is different from helium, that's different from lithium, boron, carbon, nitrogen, and oxygen. Their properties are not only mass, but also the way they react with other atoms forming molecules, and so on, so on, so on. But in the type of situation we are exploring now, light interact with atoms in a very specific way. And here try to explain in a very simple way how that is done. So you have atoms, they have energy levels, and electrons are bound, are forced by the laws of quantum mechanics to occupy one of these energy levels. They cannot stay in between. Like, I cannot take this electron and put it right where my cursor here is. So there is a high probability of having electrons here or there, which means when energy or light comes along and pass close to this example, this type of atom, if light is capable of bringing enough energy so that electron goes from level 4 to level 5, then electrons will go from level 4 to level 5. And what happens is the electrons stay there for a little while and then decay and then undergo a process we call cascade, and then cascade down to level 3, level 2, or level 1. And when it cascades down, it sends out light, sends out energy. So light energy can be absorbed by atoms, selectively speaking, creating lines, absorption lines. But after this absorption takes place, atoms can also undergo this excitation, and these electrons will be forced down and as they do force to occupy, to populate lower energetic levels, they send out very discrete packets of energy, energy of certain specific wavelengths or colors. And here's an idea. Let's see if I have a better one. So let's say you have a cloud that is being excited by a nearby star that is producing enough energy of its own, ultraviolet radiation of its own, so that this cloud has a bunch of hydrogen that get excited from its ground level, right? And when so the star itself is giving you ultraviolet radiation, the cloud glows and hydrogen get excited, and when hydrogen undergo this excitation, it produces these green photons that goes in every single direction. If you happen to have a telescope pointing at that cloud, that has a detector that allows you to measure light in that particular color band, see what you got? You got an emission line. Okay, so emission line is some package of energy a cloud is producing that is more energetic than the background light from which originated. Here's an example. You have a light source like a light bulb that can produce light of all possible wavelengths, and then a telescope collects those, and now you have a rainbow and you have all colors available. But let's say you have between this light bulb, you have a cloud like an atmosphere, like our own atmosphere, like the atmosphere of a star, and this light is the interior of that star. Now, but this cloud is made of certain particles that love these green photons. So which means it ignores all the other color bands except the green photons. And what you're going to detect in your rainbow, because originally this light bulb gives you a rainbow, it's going to provide you with an absorption line. So absorption lines and emission lines are the means, or in fact this technology is called spectroscopy, is a technology that allows astronomers to infer that certain clouds have hydrogen or calcium or boron or neon or any other atoms as a result of this interaction between light and matter. Okay, and then you have all these millions. See these little black lines in there? Those are absorption lines. They're on display in a rainbow that has been collected from a star. Here I have more specific display of these rainbows. So if you are a student and you are learning astronomy, one of the first major things you learn is how can you learn to identify these transitions. So how broad these transitions are, these lines are, will tell you how populated with atoms that particular cloud is, if the atoms are moving with certain velocity or not, and if there are displacement in the central peak of this line, the central dip of this line. This is telling you if this gas is moving away from you or towards you, all kind of things. Okay, so again, you don't go to the cloud and take a picture of it. You do spectroscopy, you create a rainbow of that particular cloud, and then you analyze in detail transitions of that cloud. One of these techniques is called Doppler effect, and one of the class work that I have set is based on that. So Doppler effect, astronomers observe, for instance, the dip of these lines and see how, in respect to a laboratory dip, the one that is here on Earth at rest in respect to Earth, if that dip is blue shift or red shift. So get used to these terms. So blue shift means the gas that's producing that light is moving in respect to towards you, or you and that cloud source is moving towards each other. So we have a relative motion between us observer and the cloud, in which we are approaching each other, and um, we can detect that as a blue shift. And red shift is when the central part of the line move towards longer wavelength, indicating the cloud or as observer are moving apart from each other. So the animation that I sent it to you explains and try to mimic all of that. So photometry is another technique. Photometry, so spectroscopy, is you create a rainbow of the light source of your object, and then you analyze these millions of transitions, absorption or emission lines. So this is called spectroscopy. You can use that to infer temperature, to infer gas motion, to infer activity level, all kind of things. The other technique is photometry. So photometry is what? Is you have a detector that detects the intensity of light. You can have a spectrophotometer, which means a photometer that is sensitive to the light brightness in different color bands or in different frequencies. But the general idea of photometry is this: you keep mapping how bright or dim the light source becomes as a result of interaction with some external source. So you just map brightness fluctuation in the stellar source, and then you can infer properties of the star. Here's an example. You have two stars eclipsing each other. So this is the first picture taken, and you have this intensity level. But when the star, the blue star, is transiting the bigger red one, see what happened? So there is a gap, there is a dip in the intensity level. So in fact, when the blue star start transiting the big one, so they can use the depth of this source to find out how big this secondary star is. They can analyze this shift here, how long it takes to be completely eclipsing, to also establish the size of these eclipsings, this transiting star. And here in this part they go back to the original level, and here the blue star is transiting, is hidden from view, and then you have a bigger gap, a little bigger diminishing in the intensity source of the system, because the blue star is the one that is more intense and that is being blocked from view. And then it goes back to normal, and here back to the transit. So astronomers can just take a photometer, point to a star source, and then they can infer properties in there. In fact, Kepler satellite is one that found thousands of new planets in a very small region of the sky using basic photometry, by finding out how the dimming level of certain stars as a result of a planet transiting the disk of these stars. So the last thing that I would like to emphasize is the so-called HR diagram. So Hertzsprung-Russell diagram is a diagram that relates energy produced by the star and their surface temperature in a way that surface goes from the hottest one is in the left hand side and the horizontal axis, and your y-axis is in a logarithmic scale. So when you plot stars for which you know their intrinsic luminosity, their energy production, and how hot they are at the surface level, you realize that 90%, 90% of the stars or more in our galaxy, they happen to be what's called main sequence stars. And the remaining 10%, some of them are giants, some of them are supergiants, some of them are white dwarfs. So why is that? So astronomers realize all these different classifications, like main sequence, giants, subgiants, supergiants, or white dwarfs, indicate different phases of stellar evolution. So with HR diagram, we are entering the realm of stellar evolution, and we are going to learn that what determines, what controls the evolution of a star is its mass content. Massive stars, they evolve quicker and faster than low mass stars. And most of the stars in our galaxy are low mass stars. The majority of them are low mass stars. Okay? So Lorraine, I'm gonna pause the tape now.